first course, we are dealing with the first part of transformers. As you can see, this is the whole architecture of transformers. But here we are going to start with inputs and inputs embedding. So when we ask ourselves what are inputs and embedding, well, inputs are actually the data that we are going to use in the architecture itself. And the data could be a sentence, multiple sentences, a paragraph, or a huge corpora. So we are the ones to decide the size of the data. And then we have an example in here. Let's look at the example. I have defined a variable in here, and it contains a string, and that string says the transformer is a revolutionary NLP model. And when we tokenize the sentence, and we have to define tokenization, but it's going to be a long story. So long story short, tokenization is splitting the words into multiple elements in a list based on so many criteria. So the first thing that we can notice in here, the text must be written in lowercase forms only. The second thing, as you can see here, transformer is actually a noun, but here it returns everything to its basics. So as you can see, transform is separated from er in here, and we have is in here, we have a, revolutionary is a single word, it cannot be separated, NLP, model, and then we have the mark. So this is the implementation of tokenization. It is very important in the initial step or initial steps to work with transformers. We have another example in here. This is another input, and it's defined in text as well. So the cat slept on the couch. It was too tired to get up. So when we embed the data, or sorry, when we put the data in the embedding process, we have to represent the text with numbers instead of using words themselves. Because one time I tried to rely on words only in Markov transition matrix, and the process killed my laptop, even though it was a gaming laptop at that time. So I had to map the words with numbers, and the computer is going to rely on the numbers. So when we duplicate the words or use them over and over and over and over and over again, the computer is going to be tired. And let's say the computer take each word, even though it is repeated or duplicated, and it gives it a special ID. And then after doing the whole process, the computer is going to use the full capacity of its power, and then it will be very slow, or the process is going to encounter a crash, so it's not going to complete the whole process and will stop in there. But when you give each word a number that represents it, so each number is given an ID. So when we repeat that number over and over and over again, we use the same ID that is stored in the computer. Hopefully you did understand me. So I did try to simplify everything, but if you don't understand, just skip this part and move to the next part. So before we get started with coding, I just want to clarify that I am using a paid service from Google Colab, and that is to speed up the process. Of course, if you rely on the regular service without any subscription, the whole service is going to be very, very, very slow, and maybe you won't be able to continue your work, and maybe you're going to skip the whole course. So my recommendation is try to subscribe with the lowest paid service. So just to make everything clear, I used this service, pay as you go, because I don't like to subscribe. Yeah, maybe I said I did subscribe. No, actually I used this service, pay as you go, and the amount I paid actually was about $20. So $20 or $10 is totally enough to train a small model and do this course. But if you are newbie, or maybe you're going to retrain a model over and over and over again, you have to have a budget so you can spend it on training itself, and this is going to be costly for you. So my recommendation is try to do the course with an extra care, so you don't make any mistakes and then lose too much money. This is it. And actually, the GPU I am going to use in this course is 800 GPU. As you can see, the difference between other models and this GPU itself. We can see T4, it's actually put in here. This is T4. Yeah, T4 GPU, this is T4 GPU. And you can see the whole comparison in front of you. I'm not really sure if this comparison is implemented or applied to this one here. Maybe there are differences. Maybe this the model itself of 800 GPU is different from this one, so I'm not really sure. But this one, I just find out that 800 GPU is very fast, and it takes maybe a few seconds compared to a few hours with other GPUs. So let's get started with coding. To make everything simplified, I am going to use Gensim, and it is data based on news from Google, and it has 300 vectors. What are vectors? We'll get to them. Let me import data. Okay, and then let's load the trained data on the Google News dataset. So now I'm going to run this cell, and it is going to download about 1 giga and half, or 1.5 giga, 1.6 gigabytes of data. So this file is not large compared to other files, of course, but we are going to get started with it anyways, because it is going to simplify everything for us. As you can see, it's taken too long, so I believe that I didn't change the hardware accelerator. Yes, of course, I didn't change it. So I'm going to change it now. This will affect my work, and it will start everything from the beginning, and this is totally fine. I'm going to rerun the cell again, but I have to wait for the connection to be done. So it's about to be finished. Yes, it is finished now. And if you want to see the capacity that we have, so the system RAM is 83 gigabytes, the GPU RAM is 40, disk, this is the disk, about 100 gigabytes. So I'm going to run the cell again and notice the speed of the process. Again, I'm going to click on this, and the model is going to be downloaded now. Look, it's taken too long, even with this one. So I think even though we have a faster GPU, this one is not going to be reflected on the size of the data downloaded. So it's going to be the same, because yeah, when I did try CPU, it was actually about this fast, maybe a little bit slower than this one. And I thought when you upgrade the service or upgrade the GPU, they would give you more speed so you can download the data, but unfortunately, as we can see, it's not that fast. So we have to wait until the data is fully downloaded. Okay, great. So almost there. Now the model is going to be downloaded on Google Colab, of course, and it's going to be temporal, so it's not going to be there all the time. So you have to make sure when using Google Colab, you have to understand that with each session there's a temporal data that is going to be downloaded, and once the session is done, the data is going to be deleted directly. So make sure to save your data somewhere else, like on Google Drive, and then you have to link your account on Google Colab with Google Drive, and then you have to import the data from there, and like this you are going to be able to save your data. So the model is done, but apparently the last step of the process is going to be, yeah, it's done now. So the loading part is done. Now let's run this part, and before we running it, I just want you to understand that we are going to get the embeddings of each word. So what are the embeddings? At the beginning we said the Google data based on the news are done with 300 vectors. So each word that we are going to input, we will get its embedding. So we're not embedding a word. Now we are going to get the embedding of the word from the model itself, and that model represents a single word with 300 floats. As you can see, this is a float, this is a float, this is a float. So each float is going to, or the whole floats are going to represent a single word. Let's look at the word computer, or you know what, it's written here brown and black, but why not? Let's try with computer as well. So here I'm gonna put embedding 3 equals model, and then I'm going to include the word computer. Okay, but before that, this is the word computer. So let me just comment out this one and work with the two words we have. I am going to see the similarity of the word black and brown. So let's click on it, and we are going to get the same data existing before. So the number of vectors are 300, and I use here print plus len to see the length of the data, and this is the whole data that we wanted to see. Now I'm going to make another cell and here I'm going to take this part that I did write before and put it in here and remove and yeah, return it back. So we'll remove the comment in here, and let's just write embedding 2 or embedding 3 and see the embeddings. Yeah, so these are the floats of the word computer. Now, since we know the embedding process or the embedding of that word, now let's move to another process to see the similarity between black and brown. Since we are using Gensim, well, the data here are not huge, so the output is not going to be that great. So let's click on it and see. So the cosine similarity is 0.7, so it's about it's about 57% of similarity. Now we are going to load another model, okay, or pre-trained model that is called RoBERTa, and RoBERTa is actually a fine-tuned model that was once called BERT, and BERT was a revolutionary model in the area of natural language processing, and it was one of the initial models that existed in the beginning, and so many scientists started using it and fine-tuning it until they got so many forms of it before the existing of GPT-2. I'm going to load the model, and this is of course going to take a very long time. So we have to use from transformers import RoBERTa model and RoBERTa tokenizer. So this time we are going to load the model and load its tokenizer, and apparently it's doing that so fast, so we have to wait until the whole things are done. Okay, apparently it's done. And this time it is so fast. I don't know why, but yeah, it's much faster, and probably because I used transformers. I don't know, but if you don't have transformers, if you are using your regular computer, you have to install transformers at the beginning. So I forgot to say that, but I have to click on. Sorry, I have to write pip install transformers. Okay, and like this, you're going to install transformers on your computer via RoBERTa if you don't have it. But since we are using Google Colab, the model is pre-downloaded in Google Colab itself. Now we are going to move to other parts, but before we do that, let's load the pre-trained RoBERTa model and the tokenizer itself. So the model name is going to be called RoBERTa large. This is what we did actually, and then the tokenizer part, or the tokenization implementation, is going to be via RoBERTa tokenizer dot from pre-trained, then the model name. So this is the model name, and then this is the model itself. Now we are going to import torch. So just import torch, and then we are going to discuss that later. But for now, we have to tokenize the two words that we used previously, the word black, and we have to tokenize also the word brown, and see the returned, or the output of those tokenizations. So after that, we have to embed the tokenized words by using this code, of course. So it is with torch dot no grad, and then I have to pass through these two words. Embedding black equals model input ID is black, and then last hidden state, and the same thing goes with brown. And finally, after doing that, the vectors are going to appear in here. So we have to save the vectors in this variable black vec and then brown vec. So black vec equals embedding black, and it is going to be the last one. So as it says in here, we take the embedding of the first token, and the first token as the representation of the word. So this is the part that we are going to get the embedding, let's say the vectors that is going to represent the two words, embedded vectors, of course. Okay, we're done. Now let's print out the representation of the word black and the representation of the word brown. Okay, good. Now, I just wanted to know what is the size of the vectors of RoBERTa. So I'm going to write print, and then I'm going to write ling, and then I'm going to write black. And of course, this is going to be the same with brown. So pick one of these and then click on them. And after that, you can see the size is totally huge, different compared to Gensim from Google. So Google used 300 vectors, and RoBERTa is based on over 1,000 vectors. And this is actually good. So I am thinking, what's gonna happen when I do the similarity or the similarity process with these two words? So we are going to convert the outputs to arrays, and then we are going to run the similarity process. So now they are converted from tensor to arrays, and then I'm going to run the similarity cosine or cosine similarity part. So let me run it now, and we can see that the cosine similarity is 0.99. So this one is totally different from the previous model. This model is let's say much stronger, much better than the previous one, and it's much larger compared to the previous one, and it has more vectors, and the vectors are actually the embeddings of that word brown, and the embedding of that word black, and thousands of, or 1,000 of vectors are actually the representation of a single word. And when we have more and larger and larger vectors, that means we have a better model actually. I'm not really sure, so we are going to test my theory in the next courses. So this is another implementation of the cosine similarity. If we want to use it, it outputs almost the same number in here, but there is a little difference in here, but the overall number, yeah, is closer to the previous one. Thank you for attending this lecture, and see you in the positional encoding course. Goodbye.